Hi, class. So we're going to look at thermal reactions or thermochemistry. All right, so now let's look at thermochemistry and mechanisms. So what we want to think about is we're going to talk about reaction mechanisms. So this is a step-by-step description of how reaction occurs. So what you're going to start to see is us use arrows to say where electrons are moving, right? So how does a new molecule form? How are bonds made or broken, right? And so these reaction mechanisms tell us a step-by-step process of how you get from one molecule to the second, right? And you can almost think of it as like you're watching a YouTube video and a step-by-step process on how you build something, fix something, and it's going to show you step-by-step how we got from one molecule to the other. Now, we do a couple different things is a lot of these reactions, what we're going to be concerned with is the energy, right? So the energy of the system, both in terms of how much energy does it need to get the reaction started, right? We're going to talk about an activation barrier, right? So how much energy does it need to get started? And then at the end, whether the reaction is endothermic or exothermic, right? So exothermic means energetically favorable, so it's going to give off energy. Endothermic means it's going to take energy in. One of the ways we can do this is we can look at a reaction coordinate diagram. And so that's actually going to show us a graph where energy is on one axis, and then time in terms of how the reaction is taking place is going to go across the axis, right? So energy is plotted on the vertical axis, or what most people can do, the up and down, right? And then the reaction progress is plotted horizontally, right? So across. So you're starting at point A. What does molecule look like when it's finally done? Okay. One thing, and we'll keep coming back to this idea, especially as we talk about different types of reactions. Most chemical reactions work because they're colliding into each other, right? So molecules, if you have two things being added, they've got to bump into each other, right? They've got to have these collisions. You'll see when we're in lab, we actually put a round bottom. When we have reactions, we'll put a stir bar, and the stir bar mixes it, right? So it forces those collisions to happen. All right, so typically we need the molecules to bump into each other to get those reactions. When they collide and yield a reaction, at some point, the molecule's transitioning from point A to B, right? So that transition state is what usually means there's some bonds being broken or formed. And so that's kind of that pivotal point of switching from molecule A to B. All right, so let's look at that. So one of the things we can look at is our energy here on the left, reaction coordinates. So I mean, we're starting with A and we're getting to B. The way this works is we're just looking at an acid-base reaction. So over here, HA is your acid. And remember, an acid is a proton donor. So we have our proton, and our base is a proton acceptor. So the base is going to get this proton. And it also means that the acid is going to be that proton donor. So we start here with our two reactants. Here's our acid with the proton that is going to highlight it. And our base is going to pick it up. So we're at some energy level. This is the energy that it's going to take to get over, right? So this is our activation energy, right? The bigger that activation energy, the harder it is to get to there. So what happens is in our transition state, as that base is grabbing that proton, we're breaking that bond between the proton and the acid. What these dotted lines symbolize is the bond being broken, right? And actually, it's being broken to the acid, it's being formed to the base, right? So as the base, and let me put these arrows because this is the way we would see it when we're just drawing them, the base would be reaching out and grabbing that hydrogen, and we push those electrons on the acid. And so that's exactly what we see is the acid is losing that proton, the base is grabbing it. The other thing is you have these partial charges. So when we lose that proton, remember a proton is a hydrogen without its electrons, we put those electrons back on the acid. And so if we put them back on the acid, we're slowly putting them on so they have a negative charge. And at the end, you see the acid has a negative charge. Right? If the base had a negative charge, right? Let's say it had a negative charge again, like it was sodium hydroxide. As it's grabbing that proton, it's losing that negative charge. So in this case, it went from a full negative charge. All right, so let me draw an actual molecule. So let's say we had HCl. And we had sodium hydroxide. As that negative charge, right, is grabbing that proton, and this is pushing on, while the chlorine is going to gain a negative charge, we're going to lose it here. Now, we don't indicate the loss or gaining of that negative charge. We just show them transitioning from no charge and a formal charge into this in between. Okay? At the end, when that hydrogen is starting to be transferred all the way over, we get to our product. So there's the base, right, that has picked up that hydrogen, the acid that's lost it. So if we draw this, we have water plus our Cl minus. Okay? And so this would have been my acid that's here. And then this would have been my base. All right, so not too bad. So we're just going to kind of move forward through these reaction coordinate diagrams. Right. One of the things we'll talk about later is the way if we use a catalyst, right, we can get this energy down. And the other thing we can talk about is the free energy here. So our delta G is telling us whether this reaction is exothermic or endothermic. So since it's lower than where we started, it's exothermic. If it had been higher, then it would have been endothermic.